pulsating radio source, a pulsar for short, beats out this rhythm far away among the stars. It's a star utterly crushed by the force of its own gravity. In the thousands of years for which men have wondered about the meaning of what goes on in the sky, there's never before been so dramatic a period as this. When the pulsars turned up just over a year ago, the Cambridge radio astronomers who discovered them were so astonished that they labeled their first records of these regular pulsars LGM. That stood for Little Green Men. It seemed at first less incredible to think that intelligent beings elsewhere in the universe were trying to get in touch with us than to imagine that a star could produce this jazzy rhythm. The pulsars are just the latest in an extraordinary series of discoveries made in the past few years. All over the world, astronomers have spotted events of breathtaking violence, scarcely explicable in the known forces of nature. They are also on the brink of establishing for the first time the history and fate of the universe we live in. That's why we've invited you tonight to come with us around the world. We shall visit the great observatories and meet the astronomers who've opened new windows on the universe and who are making the major discoveries. Our story also involves a Japanese teacher of classical guitar. A huge tank full of dry cleaning fluid a mile underground in a gold mine. An astronomer who flies a telescope 10 miles up. A strange-looking horn that's said to have picked up an echo of the Big Bang with which some say the universe began. In England, they think they've found a horizon of time before which the universe had no stars. This American foresees that the heavens will truly fall one day and bring our universe to an end. In a way, it was this Dutch astronomer, living with his family in California, who started the present revolution in astronomy. Martin Schmidt was the first man, 6 years ago, fully to realize the violence of which nature is capable. He's just setting off for Palomar Mountain, where he'll use this giant telescope to gaze across the oceans of space and time. Later, we'll join him there. We're not only going round the world, we'll be traveling out into the great void that starts just above our heads, to the storm-swept sun, out among the stars to see their violent births and even more violent deaths, to distant galaxies, vast collections of stars like our own Milky Way. Incredibly enough, galaxies sometimes explode. And going on, out as far as the human eye can see, we'll examine the evidence that the universe itself began with a Big Bang. You and I are products of the forces of nature, operating over thousands of millions of years. The upheavals which astronomers speak of are creative as well as destructive. We are children of a violent universe, and that's why what happens among the stars is a matter of intimate interest to us. This is the golden age of astronomy, and tonight the astronomers want to share their excitement with us at a rare moment of discovery such as may never occur again. And to help guide us among the new discoveries around the world of the astronomers and through this vast universe, we have with us Carl Sagan from Cornell University.
Our sun is a star. It seems large because it's so close, but for all that, it's a humdrum and quite ordinary star. We've modeled the sun and the nearby stars. Here, this star that's blinking is our sun. Near it are the neighboring stars in space. Because of our vantage point near the sun, we're able to recognize the familiar constellations of the night sky. To the north, we can see the Big Dipper, pointing towards the pole star. Near the Milky Way, we can see the familiar winter constellation Orion. If you live in the southern hemisphere, you'll recognize the Southern Cross. Let's take a stroll among the stars. Let's amble north. As we do so, let's keep an eye on the Big Dipper. Notice how its shape seems to change as our perspective changes. The reason is that the Big Dipper is composed of stars, some of them intrinsically bright, but rather far away, some dimmer, but closer in. The constellations that seem to be points of light painted on the vault of the heavens are really composed of stars at a variety of distances. And if there are creatures that live on planets of other stars, they will see different constellations in the night skies than we do. Well, we've reached a star which astronomers call Gamma Cephei. It's so far from the sun that it takes light some 50 years to travel from the one to the other. The earliest signals of our technical civilization on the Earth are only just now reaching Gamma Cephei. These signals are the earliest radio broadcasts, perhaps an aria of Enrico Caruso, but we do not know if there's anyone here to listen. Let's take a look back the way we've come. Let's try to see if we can recognize where we've come from. Which of these stars is the sun? The sun is such an insignificant star that we can't make out which of all these stars it is. In fact, the only way we can do that is to ask it to blink for us. Blink, sun. There it is. We can now amble back towards home. As we do so, we can recall that these points of light in the sky, every one of them is as mighty a star as our sun. Let's head home to our familiar solar system. As we do so, we can recognize the planets accompanying the sun. Looming up is the giant planet Jupiter, a gassy planet very different from the rocky and metallic Earth. As we move inwards from Jupiter towards the sun, we can make out the red planet Mars, a possible abode of life, the target of 2 American space vehicles now on their way to explore Mars. If we continue further inwards towards the sun, rapidly passing by our home planet, we reach Venus, a cloud-covered planet with a searing hot surface. At the present time, there are 2 space vehicles launched by the Soviet Union, which are headed towards Venus, perhaps to land there. Let's now return to our comfortable and cozy home planet, the Earth, with its tiny moon which circles it.
This is the year of Apollo, when men may first set foot on the moon. It's an extraordinary enterprise, a first step into the universe. But distances in the universe are so vast that they're often reckoned by the time light takes to cover them, at 186,000 miles a second. The moon is a little more than 1 light second away, and light from the sun takes 8 minutes to get here.
In our little excursion among the stars, we traveled a total equivalent distance of perhaps 100 light years. Later on in this program, we'll be concerned with immensely greater distances of billions of light years. Compare that with the tiny 1 1/3 light seconds between the Earth and the moon. Astronomers worry about 2 very large questions. How does the universe work, and where did it come from? In this program, we consider both these questions on the nature and the origin of the universe. The first question is an attempt at understanding what we see in the sky in terms of known natural laws. Why does the sun shine? How do stars evolve? What's the explanation for these extraordinary cosmic explosions which astronomers are detecting with appalling regularity? The second question is an even deeper one. Is it possible that the universe was made instantaneously from nothing at some remote epoch in the past? This is the view taught by Babylonian astronomers, and it's familiar to us from Genesis 1:1. Its modern astronomical version is called the Big Bang theory. Or is it possible that the universe had no beginning, that it's infinitely old, as some Oriental religions teach? One modern astronomical version of this theory is called the steady state theory. We consider both these theories later in the program. We begin with the forces of nature and how they work in the stars. We'll encounter 3 principal forces. The force of gravity, which holds stars together and keeps their insides hot. Nuclear forces, which produce starlight in the insides of hot stars. And magnetism, which in a way is the least potent of these forces. And yet, look at this soaring, awesome surge of hot gas rising some tens of thousands of miles above the sun, guided by the sun's gravity, by the sun's magnetism. In this picture, this tiny circle represents the size of the Earth. It's to scale. In a way, it's a lucky thing that we're not this close to the sun. To further examine such disturbances on the sun, we go first to a unique observatory in Australia.
At Kalgoorlie, in the outback of New South Wales, a remarkable new telescope watches the sun. 96 dishes deployed in a 6-mile circle operate as one huge instrument, collecting the radio noise that tells of the violent explosions on the sun. Radio telescopes have a particular knack of picking out violent events in the universe. The reason is that hot blasts of gas caught in magnetic fields make powerful natural transmitters of radio waves. Many of the radio sources in the sky are extremely far away, but the sun is the nearest place in the universe where astronomers can see natural forces at work with a ferocity quite unknown on Earth. The radio noise comes from high up in the hot atmosphere that surrounds the sun. The surface layers of the whole continent of Australia could be blasted from here to the moon if the force of the greatest explosions on the sun were let loose on Earth. These flares, as they're called, also provoke outbursts of radio noise. 200 miles of wire carry the information about the weather on the sun from the circle of dishes to the electronic heart of the telescope. There they disclose the state of the sun's atmosphere in a motion picture. The circle represents the sun as you and I see it. The bright patches above it are radio outbursts. This unique instrument was conceived by Paul Wild.
When we were building this telescope, we had no very clear idea what to expect in the way of results. You see, we've been studying the radio waves from the sun for many years, but always by indirect means. And the thing that we really wanted all the time was to get radio pictures of the sun. And now, at last, we have radio pictures of the sun, and the first year's results, in fact, have been very rewarding and given us a lot to think about. The sun is pretty active at the moment, but the first really interesting result that we got occurred on February the 25th, 1968, at 4 hours Universal Time. The bright patch there is a radio burst which occurs immediately above a visible solar flare. The flare had started some minutes earlier. The radio burst was actually caused by a shock wave traveling upwards from the center of the flare at a speed of about 1,000 miles per second, eventually reaching the height where radio waves are generated. Now a second burst occurs, more than 500,000 miles beyond the edge of the sun. This happens immediately above one of those rising arch prominences. This prominence had been triggered into eruption by the arrival of another part of the same shock wave, this time traveling across the face of the sun. This record quite clearly demonstrates how one event on the sun can trigger another, even though they are separated by 1,000,000 miles. This new technique of being able to photograph what is going on high above the sun should help us disentangle many of the problems associated with the activity on the face of the sun. In particular, I'd like to know the basic cause of flares, which are by far the most violent events in the whole of the solar system.
In Arizona, at the Kitt Peak National Observatory, astronomers trace the origins of flares to the visible face of the sun. The most powerful optical telescope, specially made for solar work, stands like a great sundial on the mountaintop. The biggest flares on the sun flood the surroundings of the Earth with atomic radiation, which may be a danger to astronauts and even to passengers in high-flying supersonic aircraft. On top of the tower at Kitt Peak, a flat mirror tracks the sun as it moves across the sky and casts its light into a tunnel. The tunnel slants down for 500 feet to the big reflector embedded deep in the mountainside. The sunlight, now focused, returns up the tunnel to the observation room, where it forms the largest image of the sun available for study by astronomers anywhere. The most conspicuous signs of storms on the sun are dark sunspots. As the spots sweep across the large black hole, detectors register strong magnetic forces in their neighborhood. Magnetism in the sun's atmosphere above a sunspot is recorded by this pen. At 93 million miles range, the sun betrays its stresses. Here's how the trick is done. Beneath the ordinary-looking tabletop is a 65-foot spectrograph, which finely grades sunlight by its colors and wavelengths. Magnetism at different levels in the sun's atmosphere reveals itself in subtle effects imprinted on light of particular wavelengths. From the data recorded point by point across the face of the sun, the astronomers can have charts made up. The mosaic reveals a jungle of magnetic zones and the strong fields of the sunspots. Magnetic contortions around the sunspots cause energy to build up, the energy that suddenly bursts out in a violent flare. The colors of the mosaic indicate the strength and direction of the magnetic field at each point. And it's between close pairs of zones, shown by contrasting colors, that a magnetic loop can form, which propels the stuff of the sun high above the surface to make these extraordinary prominences. The surface fireworks of the sun are very impressive, yet the magnetic energy involved is almost insignificant compared with the nuclear energy at the heart of the sun. Machines called accelerators show on a minute scale how nuclear forces work in the sun and the stars. William Fowler of the California Institute of Technology is a pioneering investigator of the nuclear life of stars.
The observational astronomer works at the telescope. Experimental nuclear physicists, like myself, works at the accelerator. I think it's fair to say that we've learned as much about stars at the accelerator as we have at the telescope. Here in this laboratory, we study the nuclear processes that take place in the sun and in other stars. These processes generate the energy with which the sun shines. All of the light and heat that has fallen on the earth from the sun was originally generated deep in the sun's interior. This energy generation takes place through the transmutation of the element hydrogen into the element helium. Nuclear processes not only create energy in stars, they create new elements. Turns out that in other stars, and eventually we think this will happen in our sun, helium is being converted into carbon and oxygen, these elements into silicon, the silicon into iron, and all the way up through the chemical periodic table to uranium and the transuranic elements. As a matter of fact, we think this is the way all of the elements heavier than the primordial hydrogen were created. This includes the elements in the earth and in your body and in mine. All were formed in stars which were born, evolved, aged, and died a violent explosive death long before the sun and the solar system came into being. Now, there's some uncanny things in this chain of element synthesis. One of the atomic nuclei in the chain, beryllium-8 by name, is slightly unstable. Had it been stable, the whole chain of element synthesis would have been quite different than it actually was. And the delicate balance between the abundances of the element carbon and oxygen and the still heavier elements that were necessary for the formation of life as we know it here on Earth would just not have occurred. we would not have been here. Now, we think we can account for all of the chemical elements, why iron is common, why gold is rare. We think we know why stars can shine steadily for thousands of millions of years and then violently explode in what astronomers call supernovae. But we would like to have more direct evidence of what's taking place in stars, and in particular in the sun. That evidence is now being sought in a most unlikely place.
It's nearly 100 years since the gold rush of '76 hit the Black Hills of Dakota. Calamity Jane and Wild Bill Hickok today lie buried over the hills in Deadwood, South Dakota, and the surface gold that lured the adventurers has long since vanished. But here at Lead, the miners are still encamped. They follow the run of the precious ore far underground. It's the biggest gold mine in the Western Hemisphere, Homestake. The graveyard shift is just ending.
Hi, Doc. You caught any little stranger down there?
Wish I had.
Raymond Davis, a chemist from the Brookhaven National Laboratory on Long Island, does his astronomy in the depths of the mine. Just one assistant goes down with Davis to the underground laboratory. No sunlight reaches a mile underground, nor do X-rays from the sun, nor even the atomic bullets of the cosmic rays. No radiations pass unhindered through such a roof of rock. Nothing, that is, except the most ghost-like of rays, which are called neutrinos. They breeze right through the Earth.
Ray, if you'll take these, I'll turn the cooling water on. Okay.
100,000 gallons of dry cleaning fluid fill this tank to catch neutrinos coming from the very heart of the sun. The neutrinos are so elusive that other rays would swamp any detector. That's the reason for taking refuge with the gold miners. But though they're hard to detect, there is a way. Some neutrinos do react with atoms of chlorine. The liquid in the tank is mostly chlorine. As vast numbers of neutrinos stream through it day and night, a few react with heavy atoms of chlorine. Every 3 months or so, Ray Davis comes to Homestake to gather a harvest of neutrinos. More precisely, he collects the atoms that have stopped neutrinos. That interaction changes the chlorine atoms into a radioactive gas, a form of argon. In his underground laboratory, Davis prepares to extract the argon atoms. A trap cooled with liquid air is part of the system for collecting the telltale argon. Helium gas roars through the tank, sweeping out any trace of argon. When the gas stream circulates to the laboratory, this cold trap freezes out any vapor that's mixed with the gas as a first step in purifying the argon. It's a week's work purging the tank of its traces of argon. The cold traps have done their work of collecting and purifying the argon gas. Now it's been released from the last trap. Pressure of mercury shunts the gas through the pipework. The gold miners along the tunnel digged several tons of ore to win an ounce of gold. Similarly, the purified yield from the huge tank is a little argon gas containing a very few radioactive atoms that tell of neutrinos caught during 3 months' watch on the sun. The radioactivity will be measured in Davis's home laboratory, 1,500 miles away on Long Island.
When we designed this experiment, we expected 5 to 10 neutrinos to be captured in this tank every day. Our measurements so far show that less than 1 day. So this means that the center of the sun is not as hot as we thought it was. Maybe it's 1,000,000 degrees cooler than we thought.
You know, Ray's tank is really a gigantic thermometer with which he's taking the sun's temperature. So far, he's told us that the patient's temperature is less than what all we doctors thought. But we don't think we're going to have to change our general ideas of the structure and the nature of the sun. We think if Ray improves the sensitivity of his equipment, he'll find the neutrinos all right. But I have to confess to you, we've got our fingers crossed.
For astronomers, the sun is conveniently near for examination, whether they're looking for neutrinos from its center or watching the magnetic upheavals on its surface. This unusual picture of the sun was taken from a rocket by a company called American Science and Engineering. The bright spots are stormy regions that are emitting X-rays, intense rays that are stopped by the air, so that you have to get your camera above the atmosphere to take such a picture. Looking at the sun helps astronomers to understand much more distant stars. But by looking out at other stars which come in all sorts of sizes and conditions, young and old, hot and cool, astronomers can work out the history of our sun